I would like to welcome you to today's ACIL webinar, Air Analysis, Understanding Thermal Desorption. Before we begin, I'd like to review a few points of protocol so that you'll get the most out of your webinar experience. Remember, you are listening to the webinar via a conference service. If you are disconnected, repeat the steps that were given to you by the GoToMeeting email. In order to reduce background noise, please be aware that all participant lines are muted throughout the webinar until the Q&A section at the end of the webinar. If you have any questions throughout the presentation, please type them in the Q&A panel located on the right-hand side of your screen under the Q&A tab. The presenter will respond to questions as they become available. If your question is not answered during the course of the presentation, it will be answered during the Q&A section at the end of the webinar. Please note that today's program is being recorded. Now it is my pleasure to introduce our presenters, Lee Murata from PerkinElmer and Roberta Provost from PACE Analytical Services. Before coming to PerkinElmer, Lee worked for Exxon Corporate Research as a gas chromatographer, joining PerkinElmer in 1992 as a GC product specialist. She became an expert for the environmental, petroleum, chemical, and fine chemical industries. Currently, she holds a senior scientist position focusing on the petroleum and environmental markets, helping her customers and her team be successful by developing more efficient methods and technologies. Roberta earned her degree in chemistry from the University of Wisconsin. She has an extensive and successful career in the environmental industry that spans nearly 20 years. Past experience includes wet chemistry, metals, VOCs, PCBs, organochlorine, and organophosphorus pesticide analysis, as well as industrial chemistry method development. She currently works as a senior chemist in the Air Laboratory at PACE Analytical and specializes in method development. Ladies and gentlemen, please welcome Lee Murata and Roberta Provost.
Thank you, Tony, very much. And thank you, everyone, for joining our webinar, our educational webinar today. Hopefully, everybody gets a lot out of it. And thank you to ACIL for hosting this. Roberta and I are here sitting in PACE Analytical Services headquarters in the beautiful city of Minneapolis. And it hasn't started snowing yet, so that's a good thing, although it is raining outside. Today we're going to provide a bit of an introduction, then we're diving into theory and practice of thermal desorption. We'll talk about tube design and recipes, active and the differences between active and passive sampling, how the instrument operates, how you get your analytes into the detector and into a report, which is what we want for information, some of the validation that Roberta and I have done. Then Roberta is going to get into some applications with site studies from specifically from MGP sites, soil gas, and then I'll come back and talk about the new EPA regulation and a new EPA method called 325, and then a very brief summary. So here are some of the applications for environmental analysis for air. We have soil gas, which is relatively new. The concern is when you have soil vapor intrusion, and Roberta is going to get into that in more detail. Indoor and outdoor air, the new fence line monitoring for benzene, method 325, stack monitoring, what is coming out of the stack, manufacturing gas plant sites. These are covering methods to determine toxic compounds in air, typically done by detection by mass spectrometry, or MS for short. Ozone precursor started in 1991. I think it was promulgated in 93. That's to determine ozone precursors in our environment. A lot of that's with the GC FID applications. And if you're in non-attainment, which means a state that exceeds their allowable level of these compounds, many things were introduced. If you live in one of these states, if you notice when you go to the gas station and you have an extra cap on the nozzle. That's because it's trying to recover the VOCs to try to not be in non-attainment anymore. So a lot of things came out of the ozone precursor testing. So we're focusing today on air, on toxic compounds in air, specifically TO17 and method 325. So there's a couple of methods. There's TO15, which is a canister method, TO17, which is sorbent tube method, and then the new method 325, which is sorbent tube but passive sampling instead of active sampling. TO17 is active sampling. So these are established methods. TO17 and tube analysis is more convenient and less expensive to transport. You probably could fit around 500 tubes in the same box that fits 4 cans, let's say. They're easy to clean and immediate, ready for reuse. Many times canisters take several hours to clean. Also, they require pressure testing for 24 hours. All this is time consuming. With tubes, when you desorb the tube, you get 99+% recovery off that tube. So just by sampling it, you're cleaning it. So it's extremely cost effective and good turnaround on the media. You're able to sample larger volumes. We have example of sampling 50, 100 liters, where in a can you're limited to the size of the can. Also, you typically take 500 mils from a can and not all 6 liters. Tubes have inherent water management because the absorbents are typically hydrophobic. And you can recollect the sample to preserve the sample if you need to make a re-injection. For instance, let's say if your detector saturated, you could run the tube again and establish split ratios mimicking a dilution. Also, the other advantage of tubes is it enhances recovery of higher boilers. So you're going to see examples of doing the 16 pH regulated targets going much above the boiling point of naphthalene, which is typically what a canister can get to. And of course, it's completely automated. So let's go on to tubes, how multi-bed tube works, and the difference between active and passive sampling. Well, we needed some new tube technology to deal with soil gas. So we developed, along with Caro Analytical, helped me develop this tube, and it has a boiling point range from propane or C3 up to C26 phenanthrene. And I'll get a little bit into this VOC and SVOC tube in a bit. Then, along with Alberta Innovates Technology Futures and PACE Analytical Services, I'd like to thank Roberta from PACE for helping me design the XRO 640 tube and the XRO 440 tube to deal with the volatiles plus the 16 regulated pHs. So these tubes respectively have a C6 to C40 range or a C4 to C40 range. And we're going to get into them in a little bit more detail in a bit. First, I'd like to discuss why the soil vapor intrusion tube, the SVI tube for short, was developed. Roberta is going to discuss why the XRO family tubes were developed. Well, soil vapor, it differs from other sampling. You have a high moisture content, essentially mud, greater analyte range. You're typically seeing from your most volatile gases, vinyl chloride, all the way up to diesel range, hydrocarbons, phenanthrene plus. Also, you have a wider concentration range. Unfortunately, our Earth is very contaminated, and I see concentration ranges in the milligrams. And then you have very low concentration range. So you need a you need a tube media and a method that's flexible enough to deal with all of these parameters. So that's what we were searching for. So we wanted a tube to develop a tube to deal with dichlorodifluoromethane tryptophananthrene, an absorbent to protect a weak absorbent front end to protect a stronger absorbent, and also a weak absorbent front end to recover your high boilers. And I'm going to get into that in detail in a bit, so I won't spend too much time on this slide. We achieved our goals with the SBI tube, and I call it a recipe, by increasing sampling volume while ensuring retention of all volatiles. When we were doing the development of the tube, we went to 10 liters with fast flow rates. We were able to recover our pHs that we wanted in diesel range. We were able to recollect the sample, and we were also able to do automated integrity for quality of these tubes. This is the inside of a tube. It's to deal with a wide boiling point range, such as C3 to C26 or C4 to C40. Not just one absorbent can do that for us. So in the tube itself, there's what we call multi-bed or mini absorbents, many types of absorbents. So for SBI, we have a weak absorbent, a mid-range, I should really call it mid instead of strong on the slide, and then your strong absorbent. So as you're sampling, you sample in the direction, and the tubes are marked with the sampling direction. So you sample from weak absorbent to strong absorbent, and this is pumped sampling. So you require a pump, and the pump is calibrated at the laboratory. So what happens is, let's say if you have SBI, you're doing subslab, and it's at a diesel, BTEX, gasoline contaminated site. So your C26 through naphthalene will get stopped in the weak absorbent or absorbed in the weak absorbent. Your mid-range and your gases will break through that absorbent, and your mid-range up to the gases will be absorbed on the stronger or mid-range absorbent. Your gases will break through that absorbent and be absorbed by the strongest absorbent. So now you have a situation where you're really protecting that strong absorbent from contamination of higher molecular weight species. Now, if this was a live audience, I would ask the question, why do you desorb the tube in the opposite direction? Well, you don't want to put your PAHs into the mid, or I should say drive. You don't want to drive your PAHs into the stronger or strongest absorbent because they would not recover. So this multi-bed situation allows retention of your most volatile components and excellent recovery of your higher molecular weights, such as PAHs, from the weak absorbent. So when you put your tube into your autosampler carousel, you put it in the opposite direction from sampling. So they are directional. And it's very easy to know your sample volume. It's mils, how many mils per minute were you flowing through the tube times the duration in minutes. And that equals your volume. So this is an example of a active monitoring, pump monitoring. If you could see on the top here is your pump. For this particular, Roberta and I was doing some research. These are XRO tubes at an MGP site. And we actually had a second tube in line, in series, I should say, to ensure we weren't getting breakthrough of our volatile components. So we ran this tube, which we call the breakthrough tube, to ensure we weren't getting any breakthrough, which we didn't. Going on to passive sampling, which has to do with method 325. Passive sampling does not require a pump. It has a special cap, which I'll go into on the next slide. And you could also do this for industrial hygiene with clips that hang on the lab coat of the lapels. Here you see is the tube used by the EPA to develop Method 325. This slide was courtesy of Sipalco Corp, who actually developed the CarboPack X tubes with a little help from PerkinElmer, probably around 8 years ago when all this started. And we find it important to utilize this tube in Method 325 when people are using Method 325. So if you look at diffusive monitoring, it's unique. It's very target absorbent specific. The uptake, what needs to be determined is an uptake rate. And I'm going to go into this a little bit later in the session on 325. But essentially, you have a diffusive gap, and your targets are entering that gap, and by diffusion or uptake are being absorbed by the absorbent. So only probably the first centimeter of the absorbent has the targets absorbed into it. Now I'd like to discuss a little bit about the differences between the two. Active sampling, it's very easy to ascertain the volume on the tube. As I said, it's flow rate times time equals volume. You can use a multi-bed absorbent for a wide boiling point target range. It's very easy but not necessary to use several tubes because one tube should basically do your whole boiling point range. However, it does require a pump, and again, the pump is calibrated in the laboratory before leaving. Passive sampling is excellent for long-term time-weighted averages, and that's what the EPA for the fence line monitoring of benzene at refineries is interested in. They're not interested in what happens in just an hour. They want to know what's happening in that 2-week time period. That's the purpose of this monitoring. It's easy to apply several tubes, and because they're single absorbent for passive sampling, sometimes you need a couple of different tubes with a different absorbent. The thing that's special about the CarboPack X tubes is the EPA, and it's very time-consuming to determine these uptake rates, and you need a special setup to do it. And the EPA was gracious enough to determine about 20 target uptake rates on CarboPack X, one target being benzene, and that's why we feel it's important because the EPA developed the uptake rate, and I'll get into that later, to use these tubes. So now I'd like to talk about operation of the thermal desorber itself. I've been talking about the instrument. In the instrument, again, you load your tube on the auto sampler carousel. The tube then gets placed mechanically, the instrument does this, puts it in the flow path. Before the heater goes onto the tube, the internal standard is spiked. Excuse me. The instrument can also automatically spike a surrogate, but this would be done before the tube would be sent out to sample because that's the purpose of a surrogate, right? So if you were spiking surrogates, you would put it into surrogate spike mode. It would automatically take each tube, spike the surrogate, put it back on the carousel, take the next tube, spike the surrogate. So that's not time consuming at all. The instrument can also do an impedance check on the tube to ensure that the back pressure of that tube has not changed. This is automated validation because you don't want your absorbents to be channeling, because just like water, air will take the path of least resistance. So this is a validation check. The impedance of the tube shouldn't change with time within experimental error, of course. But if you see a big change, the instrument will flag you that that tube should be taken out of service. There's also an ambient purge or a dry purge. At least 1 minute is performed on the tube to rid the tube of residual oxygen, but it also could be used as a dry purge to get rid of additional moisture. There's also an offline dry purger that we offer. We call it the tube conditioner / dry purge, so that you could dry purge at least 20 tubes at a time, plus condition them if you need to condition your tubes. After all this is performed, the oven gets placed on the tube, and inert gas goes through the tube, and with flow, time, and temperature, the targets are removed or desorbed from the absorbent, and this occurs like an exponential decay with time, just like your purge and trap like your trap and thermal purge and trap desorbs. As your targets are desorbing, they go to a concentrator trap. The concentrator trap here has absorbents in it as well. The instrument can cool to minus 35 degrees, your trap, without liquid cryogen. It uses a Peltier cooler. And if you have very contaminated samples, you could also have an inlet split. What's really nice is what I have people do is set up their calibration for the most sensitive, for the best reporting limit. If you know these tubes are from a contaminated site, like if they're from a source of contamination, put an inlet split on, but because the splits are so linear, all you need to do is put that split ratio as the dilution factor, and you do not need to recalibrate at that split setting, which is really neat. So after you finish desorbing your tube, or the instrument finishes desorbing your tube, the cold trap heats very rapidly at 99 degrees per second to get rapid desorption, which now you also have a split here where you could recollect your sample on a same or new tube, or if you're not recollecting, it just goes to a charcoal trap to vent. So usually, like for indoor air, you probably wouldn't split, or split just enough if you wanted to recollect, because hopefully levels are really low. But we could help you. We have a lot of experience in this analysis, in air analysis, since 1980. PerkinElmer have been doing air analysis. So we are the experts and can help advise you on the method. This is the schematic of the cold trap. If you notice, again, when the instrument desorbs the primary tube or the sample tube, the effluent goes into the trap from weak to strong absorbent. The instrument automatically backward desorbs the trap. So again, to get really efficient desorption of your heavy molecular weight components, here you see a narrowing of the trap. That's so that you don't get band broadening for chromatography. And again, you get, even for your most volatile components, you get very nice narrow bands for chromatography, which is imperative. Now I'd like to talk about some validation that Stefan at Caro Analytical, Roberta, and I have done on the tubes and the method. Let's talk about breakthrough. We needed to do a recipe to ensure we were getting the range we were talking about. And for the SBI tube, we're talking about the 7 most volatile components, the 2 of interest, of course, are vinyl chloride and 1,3-butadiene. The EPA defines breakthrough as if you find more than 5% of the total concentration on the second tube with 2 tubes in series. So how do we determine these? How do we do these experiments? We did 2 experiments to determine this on the tubes. For the SBI, we used a Megamix 300 nanogram spike, the VO2.2 volatile 6-gas mix, 1,3-butadiene, which comes in a separate vial, as you know, 250 nanograms of 4 pHs we selected up to phenanthrene, and 10 micrograms of diesel purchased from the local gas station. So in total, around 35 micrograms of targets were injected onto what we're going to call our spiked tube. And I say that because of the next picture. Then what we did, just with a very easy swage lock connector, we connected two tubes together. This is our clean tube. This is our spike tube that we just spiked. Our clean tube we ran first to ensure that it was clean. Or if we saw a target on there, we marked down its concentration. Now, what I did to mimic a humid environment, I used a headspace file. I put a streamline, a piping in to create bubbles, and I waited until I got about an 85% humid environment using UHP nitrogen. I didn't want to add to my targets, although in this experiment it wouldn't have mattered. And I flowed 100 mils per minute for 100 minutes, equaling 10 liters. Now, this is like a worst-case scenario because all those targets were on the tube from time 0. Typically, when you're sampling, you don't have all the targets there since time 0, right? So this is like the worst-case scenario. Roberta repeated this experiment on the XRO 440 tube. We spiked 8 micrograms and ran the same flow rate. Now, for the results from the SCI tube, we saw a 1% breakthrough of dichlorodifluoromethane. We saw a bit of chloromethane. However, chloromethane was on that tube. I saw it as an artifact on the tube when I ran it blank, but since I saw it again, I put it in the table. We saw a non-detectable breakthrough of any other target. I just put the gases here because those are what people are mostly concerned about breaking through. With Roberta's results on the XRO 440 tubes, Roberta saw non-detectable breakthrough on her targets as well. Roberta ran another experiment trying to mimic a real-world sampling event. Roberta put 2 tubes together and allowed her gaseous standard to continuously flow through the primary tube and the breakthrough tube. And Roberta allowed a concentration of about 200 milligrams to flow through that primary tube. And we got non-detectable breakthrough even with 200 milligrams on the primary tube. So we were really happy with the tube results when we're doing our validation. Next, we had to determine recovery. All right, we know we're not getting breakthrough, but are we getting the targets off the tube? So we took the spike tubes. This is an example of the SCI tube. We took the spike tube, and first we ran a blank. Then we analyzed the spike tube, which is the top chromatogram. Then we analyzed the trap. The instrument can automatically do a trap fire without running a tube. This is a very nice troubleshooting method to ensure that that your trap is not contaminated. So we wanted to make sure we were getting recovery off the trap, and yes, we did. Then we analyzed a blank tube with no absorbent in it because we wanted to make sure our instrument was nice and clean, and it was. Then we reanalyzed the spike tube because we wanted to make sure we got recovery off the spike tube. So those were the steps that we took to ensure that what we were looking at when we were checking recovery was actually the tube. And if you can see, we got recovery of, I'm only displaying the numbers for the PAHs, but we got excellent recoveries for our PAHs. And pictorially, I show this. Here's your spike tube. Here's your re-inject of the spike tube. And here's your diesel and the re-injection of that spike tube with very good recovery. Roberta did the same experiment on the XRO 440 tube. And again, we got excellent recovery or non-detectable carryover is what we're displaying here. So we were really happy with the development of the tube and the validation of the tube. Then we started looking at its performance, its analytical performance. Here's a chromatogram of dichlorodifluoromethane, essentially 8260 mix plus the 502.2 gas mix once we butadiene up to phenanthrene. So we're really happy with this chromatography. This is on a 624 phase column, and this is on the SBI tube. Here, what we did, instead of being in an eyesore and showing all, I think there are 86 or 90 targets, we grouped them into classes. So the first is the gases, and you can read the slide for the other classes within this mix. I present both R-square or linear regression and average RF because the rest of the world uses linear regression. The U.S. uses average RF. We were really happy with the dynamic range from 0.05 to 250 micrograms per cubic meter. And these numbers are well within the requirement, the EPA and other regulated requirements. Then we wanted to look at precision, so we ran 10 tubes at a 10 ppb concentration, and we were really happy with this instrument precision and spiking precision. The precision on the IS is less than 2%, and that's an automated spike, gaseous spike. And our reporting limit is guided mainly by the gases because they're the least intense. The aromatics, obviously we could get better than 0.05 micrograms per cubic meter, but we felt this was good enough. But even if you look at this signal to noise, we could do 10 less on the gases and 100 less on the PAHs. Now let's go to our volatiles and semi-volatiles on the XRO 440 tube. This chromatogram I want to point to because here we're looking at VOCs from 1,3-butadiene, including BTEX, all the way up to the 5-ring PAHs. So the chromatography, the peak shapes are gorgeous. We got normal column bleed, which is seen from a typical semi-Boer analysis. So Roberta and I were really happy with this chromatography. Roberta ran some linearity. We decided on a range from 0.2 to 50 nanograms at the time. That equals a reporting limit, as you can see, about 0.2 from a 1 liter sample volume, but we were taking 50 liters of samples, so you have to look at that too. And the precision on 6 injections is excellent. We also looked at water. This is on the SBI tube sampling soil gas. So if you don't do any dry purging, you can, as you can see, this is your water peak, and you get quenching of your gases here. When you dry purge, these dry purging recovers water, brings it essentially down to the background. So we were really happy with the dry purge on soil gas tubes. The next shows the hydrophobicity of the XRO family of tubes. With the 640 tube, there was no added moisture, even with a 45-liter sample volume. So if you only need BTEX plus and you're sampling in a very humid environment, this is a perfect tube. With the XR440 tube, we only needed a 2-minute dry purge to get it down to baseline. Well, now I'd like to, you've heard enough from me, I think, and now I'd like to hand it over to Roberta Provost of PACE Analytical Services to talk about some real-world applications.
All right, thank you, Lee. So let's take a look at some possible applications for these various types of sorbent tubes. The first one we'll talk about is fence line monitoring at MGP sites. Then we'll take a look at some sub-slab sampling. And finally, Lee will go over the new 325 diffusive sampling method for refineries. So back in 2011, PACE was approached by several MGP clients looking for an alternative to the EPA methods TO13 and TO15 for their fence line monitoring. So PACE came together in collaboration with PerkinElmer to develop a new tube and method to combine the VOCs from method TO15 and the PAHs from method TO13. A TO13 sample starts its life as a puff cartridge that must first be cleaned with 600 milliliters of methylene chloride for a minimum of 16 hours. This clean puff cartridge is sent to the client and sampled in a high volume sampler, sometimes called a birdhouse, that must be wired on site by an electrician and can cost up to $4,000 to rent. When the cartridge comes back to the lab, it's extracted with an additional 600 milliliters of methylene chloride for another 16 hours. TO15 isn't as labor intensive as TO13, but the shipping costs can be quite high due to the size of the media. Also, you can't recover targets heavier than naphthalene. By developing a sorbent tube that can be used to collect and analyze both BTECs and PAHs, the use of solvents and overall costs can be minimized. MGP stands for Manufactured Gas Plant. MGPs were industrial facilities where gas was produced from coal. This coal gas was used for lighting, cooking, and heating, and was essentially the natural gas of its time. Coal gas was used in Europe beginning in the early 1800s and came to North America in the 1820s. MGPs in North America operated for over 100 years until natural gas became the fuel of choice. The production of coal gas created toxic wastes, some of which can still be found at these former plants. Substantial amounts of coal tar containing BTECs and PAHs, acid waste, and cyanide complexes can still be found at many of these MGP sites. These wastes can migrate into the subsurface and may enter sewers, basements, or nearby surface waters. This problem is exacerbated since MGPs that at one time were located in rural areas are now near or in growing cities and suburbs, many times in residential areas. So this picture here shows the TO13 sampler right here, and we also have our TO15 canister and the TO17 manifold that we use to perform the side-by-side sampling. This table is a comparison of some of the results we obtained in the side-by-side analysis. I won't go through the whole thing because it's pretty busy, but some particular compounds I'd like to point out are from the August 16th data. We'll take a look at 2-methylnaphthalene. The TO13 result was 0.33 micrograms per cubic meter, and the TO17 result was 0.26 micrograms per cubic meter, so very, very comparable data. Also, for the August 13 data, we can take a look at phenanthrene. The TO13 result was 0.076 micrograms per cubic meter, and the TO17 result 0.55 micrograms per cubic meter. So very good comparability between the TO13 and the TO17. So let's move on to soil gas. Soil vapor intrusion occurs when toxic compounds that are present in the soil of a contaminated location have pathways of entering the building. These toxic vapors typically occur because of a contaminated water or soil source. So we'll be taking a look at 3 soil vapor sites that were sampled with 2 different types of thermal desorption tubes. The SVI tubes, which Lee talked about, which are for the analysis of a full suite of VOCs, plus the PAHs up to phenanthrene, and the XRO 440 tubes for the analysis of 1,3-butadiene, BTECs, and the full list of regulated PAHs. The first site is a commercial site where PAHs were suspected. The second site is an industrial subslab site in Michigan where 2-methylnaphthalene was an important compound of interest. This site used the XRO 440 tube and a Summa canister for the TO15 analysis. The last site is another industrial subslab site in Indiana where both the SVI and XRO 440 tubes were used for sampling. So once again, the first site is an indoor air sampling from a commercial site where PAHs were suspected. The first thing we notice is that we're able to see hits of PAHs as heavy as chrysene, which the EPA classifies as a probable carcinogen, but thankfully in very small quantities. Something else you may notice is that the indoor air concentrations are generally higher than in the subslab within the same room, which is not typical. So if we take a look at naphthalene here in the stock room, naphthalene is present in the indoor air at about 4 micrograms per cubic meter, but in the subslab at 0.25 micrograms per cubic meter. In the sewing room, phenanthrene is present in the indoor air at 1.4 micrograms per cubic meter, but is non-detect in the subslab. Unfortunately, in the lab, we don't always get to know the details of each individual site. Maybe it was someone was smoking during sampling. Or we've all heard horror stories of tenants changing their oil of their motorcycle or lawnmower in the basement, so maybe that could be an explanation. Another possibility is the very well insulated buildings and possibly poor ventilation. So in this case, we just don't know the details of why the indoor air is more concentrated than the subslab. The second site is an industrial subslab site in Michigan where 2-methylnaphthalene was a major concern. One quick note about Michigan is that they accept 2-methylnaphthalene by method TO15 out of the summa canister. In our experience here at PACE, 2-methylnaphthalene cannot be reliably or consistently recovered without some sort of intervention like canister heating. So this sampling took place in conjunction with TO15. Here we can see a significant number of PAHs that are present in the subslab environment. Most of the PAHs are at very low levels, down to the MDL even, but there are some compounds of note, like benzo-B and benzo-K-fluorenthene, which are present across the board at hits of about 0.3 micrograms per cubic meter. Unfortunately, another lab was contracted to do the TO15, and even though we contacted them several times, they never responded, so we don't have the TO15 to methylnaphthalene data to compare. However, we can still make the observation that there are clear hits of 1 and 2 methylnaphthalene using the pumped tube sampling. The third site is an industrial subslab site in Indiana. This site collected samples on both the SVI tubes and the XRO 440 tubes. So between the two tubes, a full list of VOC and PAH data was collected and reported. Additionally, the client requested 20 compounds as TICs, or tentatively identified compounds. So ultimately, this client ended up with a suite of 120 compounds, plus a breakdown of those found in the gasoline range versus the diesel range. So as we look at this table, we notice that most PAHs heavier than 1-methylnaphthalene are present mostly at levels between the reporting limit and the MDL. And you can see these two columns here list the SVI tube reporting limit and the XRO 440 tube reporting limit. These are based on a 1 liter sample volume. There are very few detections heavier than phenanthrene, but we do see a small hit of chrysene here in vapor point 114. The next thing we see in this table is that across the board, there are strong detections of naphthalene and 1 and 2 methylnaphthalene. In fact, in site VP115, the detections were so high that they required a dilution. We can also see that these hits are real since the amounts found on the SVI tube and the XRO 440 tube are almost identical. You can see here 2-methylnaphthalene on the SVI tube is 20.9 and 20 on the XRO 440 tube. Similarly, 1-methylnaphthalene on the SVI tube is present at 12.8 and 13 on the XRO 440 tube. That's an incredibly close values for a real-world sample. Those are excellent results. So these MGP and soil vapor applications show the versatility of pumped tube sampling. It's realistic that in the future we could eliminate the use of nasty solvents like methylene chloride in air analyses by replacing TO13. We can also use the pumped tube sampling to expose the presence of carcinogenic compounds like chrysene in soil vapor. These heavier PAHs simply cannot be recovered from a TO15 canister. So now that we've covered pumped tube sampling for fence line monitoring and soil vapor intrusion, I'll turn it back over to Lee to discuss diffusive sampling for the new method 325.
Thank you, Roberta. Hi, everyone. This new method, we were consultants with the EPA while this was being developed, and the predicted amount of samples per year that this regulation is going to generate is approximately 70,000. Actually, that's probably the minimum amount of samples being generated by this new regulation. I show another schematic of a passive sampling media. Again, I discussed the EPA calculated the uptake rates of about 20 targets using the Carbopac X specially treated tubes. They are only regulating benzene, so probably benzene is the only target that will be reported. However, the person may want, for their own use, want to calibrate for the full suite of 20 targets. Continuous sampling every 2 weeks. So the tubes go into the shelters. After 2 weeks, they come down from the shelter to be analyzed, and a new set of tubes get installed into the shelters. For benzene, the uptake rate calculated by the EPA is 0.67 mils per minute, which in 14 days equates to about 13.5 liters of sample. So the EPA in Part A of Method 325 gives guidance, and very established guidance on how these shelters, these sampling shelters for sampling, should be situated around the perimeter of the refinery. They define refineries as small, medium, and large. The criteria being used is the acreage of the refineries, as you can see in this Excel spreadsheet, which is taken from the method. So if you're looking at a large refinery, the minimum amount of samples that are going to be generated is approximately 832 yearly. There's about 150 refineries in North America, around 140 in the U.S., and they are all being regulated to monitor their fence line. They have up until the end of 2017 to be in compliance. So for the laboratories, they need around 10 calibration tubes. I strongly recommend you leave your calibration tubes, don't use them for sampling. Also laboratory blanks and quality control tubes for your continuing cal. What I recommend to my clients is when you're doing your standard curve, use your midpoint and spike an extra 10 or 20 tubes at that time. So it's very easy. You just pull them out of when you want to run your continuing cal, you just pull them out of the refrigerator. You store them with breath end caps so that nothing can diffuse into the tube. So it's very safe and easy just to pull a continuing cal. I've been talking about a shelter and didn't show you a picture of it yet, but this is what the shelters look like. The shelter is there to try to protect the tubes from the environment. You know, there's one thing that the shelter can't protect from is getting a hit from a local gas station. Gasoline has approximately 0.2 to 1% benzene in it. The EPA regulates gasoline. The highest it could have is 1.2% by volume. Premium gasoline usually has around 0.2%. Refineries do a good job of reducing the amount of benzene is a inherent component in crude oil. It's in the cut for benzene is in the cut for gasoline. That's why I'm mentioning gasoline. So if you have a gasoline station up the block and the wind's blowing the right way, well, you're going to get a hit from the gasoline station instead of a refinery, or if somebody's smoking near the shelter. Traffic patterns can also affect the hit on these tubes, right? It's there. But the shelters are there to protect from weather and from bugs, because you don't want to put a bug in your instrument typically. That's not a good idea. So here's the chromatography. Roberta developed this chromatogram for us. Benzene is out in 1.5 minutes. The whole runtime to get the trimethylbenzenes off the tube is, or off the chromatogram, is under 4 minutes, so very fast runtime. Again, the inject-to-inject time is very optimal. If you want to do dry purging, you could do offline dry purging, but the instrument does piggyback dry purging while it's running its chromatography to optimize time. Also, what's nice is we developed this method so that you could do your VOCs, your 525, and your VOCs, SVOCs on the same column, same trap. So you don't have to do any instrument involvement. The only thing that's involved is changing your method parameters in your computer to send the method to the GC and the mass spec, right? So that's all automated. So essentially over the weekend you could do both types of samples. Roberta and I decided on this dynamic range, consulting with the EPA. So this is based on a 13.5 liter sample volume. And as we could drop this, and we are intending on doing that, but the signal to noise at this level was about 200 to 1. So in summary, passive sampling is, the EPA is very much moving forward with passive sampling. Even for soil gas, they find a times average is good information instead of just taking a one sample for a short period of time. The tubes allow for volatiles and semi-volatiles to be run in the same analysis, which canisters struggle with or cannot do in the case of anything above naphthalene, quantitatively anyway, where the tubes can. They're hydrophobic. The instruments are very automated, which I show on my next slide. I'm not going to go into this in great detail. The spiking of the internal standard is automated. Prior to sending the samples out, the surrogate, the impedance check is another validation. Also, the tubes and traps are leak checked to ensure that for sample integrity. So if a tube leaks for some reason, there may be a dust on the tube or a hair from someone, or somebody banged the tube and it got compromised in some type of way, the instrument will put that tube back on the carousel and flag the operator that that tube leaked. It won't stop, it'll go on to the next tube, but you'll get a run log when you get in the next day that tube, there was a compromise to that tube. And also has excellent water management. So I want to thank Roberta and I want to thank everybody.
Thank you.
And Tony, we turn it over to you for Q&A.
Well, thank you again, ladies, for your presentation. Does anybody have any final questions? If you do, simply type them in the bottom of your screen, right-hand corner. Any questions? One more time, any questions? Okay, hold on, I'm seeing a question. Okay. For the refineries that are required to perform this testing, how will the testing be funded?
By the refinery. The refinery would pay for the testing, and it is already going to cost the industry a lot of money. At least we're talking about millions and millions of dollars it's going to cost the industry, but the refineries will pay for the testing.
Okay. Any other questions? Okay, we just had that one question. Let me go through. I don't see any more questions. One more time for questions. Okay. Well, again, thank you all for your participation today. Thank you again, Roberta and Lee, for sharing your information with us. And we look forward to you all joining us in our next ACIL webinar. Have a good day, everyone.